Your hand is being stopped by something it never quite hits. Put your palm on a table, and the most obvious thing in the world seems to happen. You touch it, but zoom in far enough, and that simple moment starts to fall apart. Your skin is not pressing into a sheet of tiny solid marbles. The atoms in your hand are not politely bumping into the atoms in the wood. So here is the absurd question. When you touch something, are you actually touching it? Your intuition says yes, because the table stops your hand. That feels like proof. If the table were not solid, your fingers would keep going. But at the atomic level, solid is already a strange word. Experiments like Rutherford's gold foil scattering showed that an atom has a tiny, dense nucleus, with electrons spread through a much larger region around it. Most of the atom is not filled with little pieces of hard stuff. So why does your hand not slide through the gaps? A tempting answer is, because atoms are mostly empty space and we never touch anything. You have probably heard some version of that. It sounds mind-blowing. It is also a little too simple. Because the space around an atom is not just empty hallway. It is filled with electron behavior, electric fields, and quantum rules. There may not be a hard shell, but there is still a very real boundary created by interactions. And that boundary is what your hand is feeling. Even before we reach atoms, the table is not as smooth as it looks. Under a microscope, surfaces are landscapes of peaks and valleys. When your palm rests on wood, glass, or metal, the visible contact area is much larger than the true microscopic contact area. Much of the load is carried by tiny high points pressing near tiny high points. But that only makes the mystery sharper. At those high points, what is pressing against what? The outer regions of atoms are dominated by electrons. Electrons have negative electric charge. When the electrons in your skin get extremely close to the electrons in the table, the arrangement resists being squeezed together. Part of that resistance is electromagnetic, like charges repel. But there is another rule underneath it, and it is even stranger. Electrons belong to a class of particles called fermions, and identical fermions cannot all pile into the exact same quantum state. This is the Pauli exclusion principle. It helps explain atomic structure, the shape of the periodic table, chemistry, and the stability of matter. So when your hand pushes down, the electron clouds do not behave like fogs gently mixing. Bringing them closer costs energy. The table resists. Your skin deforms. That resistance travels through tissue, nerves, and eventually into awareness. And your brain calls that resistance touch. Before we go deeper into the table, leave a comment with the next everyday absurdity you want investigated, because those comments genuinely help choose future episodes. And if this invisible atomic standoff is scratching the same itch for you, a like helps more people find it. Subscribe if you enjoy the hidden logic behind things that seem ridiculous, because the weirdest part of touch is still coming. Your body turns a force into a world. Inside your skin are specialized sensors called mechanoreceptors. They do not detect table essence. They detect deformation, pressure, stretch, vibration, and movement. When the table pushes back, your skin changes shape. Tiny structures and nerve endings respond to that mechanical force. Some signals depend on pressure-sensitive ion channels, including one called piezo-2, which helps turn physical force into electrical activity. Those signals travel through nerves, into the spinal cord, and up to the brain. Only then do you experience the table as hard, smooth, cold, rough, sharp, or soft. That means touch is not a direct window into the outside world. It is your brain's interpretation of how your own body is being distorted by forces from the outside world. So yes, in one sense, you never touch the table the way two imaginary hard particles might touch. But here is the twist. That does not mean touch is fake. It means our picture of touch was wrong. In physics, objects do not need to collide like billiard balls to interact. Forces are interaction. Electron clouds can get close enough and sometimes overlap enough for real physical and chemical effects. Energy can move, momentum can move, atoms can bond, materials can stick. In fact, take two very clean metal surfaces, remove the oxide and grime, and press them together in a vacuum. Under the right conditions, they can cold weld. No flame, no ordinary melting. Atoms at the surfaces can bond across the boundary so effectively that two pieces become joined. That is almost the opposite of nothing ever touches. And geckos reveal another version of the same idea. Their feet are covered with microscopic hairs that split into even smaller tips. Those tips get extremely close to surfaces, close enough for weak molecular attractions, often described as van der Waals forces, to add up into a grip strong enough to climb walls. The magic is not glue. It is closeness plus forces. So the popular myth needs a correction. It is not that nothing touches anything because atoms are empty. It is that touch is not what our everyday imagination thinks it is. There are no tiny solid shells clacking together. Instead, there is a rising argument between electric charge, quantum rules, surface roughness, molecular attraction, and biological sensors. The table feels still because countless tiny interactions are balancing out. Your hand feels blocked because forces are pushing through your skin. Your brain feels certain because evolution did not need you to understand electron clouds. It just needed you to know where the table was. And that may be the strangest part. The world feels made of solid things with clear edges. But underneath, everyday reality is more like a negotiation. So when you place your hand on a table, you really are touching it. Just not in the way you thought. Nothing makes sense until the table pushes back.